Hello, and welcome back again to Algebra 2 Lessons with Miss Faust. This is I don't know, I've lost count. It's early to have lost count, but another video. And today we're going to be looking at piecewise functions. So this material actually comes out of a different textbook. That's why you should have this handout I gave you in class. We're going to just talk through a little bit of it, and then your assignments will be right in this packet as well. So hopefully that'll make life a little bit easier for this section. So the first thing we're going to look at is just an application that'll help you understand what a piecewise function is and how it's different from other functions. So that's our essential question for this unit. You probably can just take notes right on this packet. You don't need to do a separate page of notes for this. That's why I've done this way. But if you're more comfortable writing in your notebook, go ahead. So big idea. Piecewise function has different rules or pieces for different parts of the domain. So we have to put together the idea of multiple domain restrictions with what we know about graphs. So this is the kind of situation that would have a piecewise function. They're actually super useful because in the real world, usually something doesn't continue forever doing the exact same thing. Things change, and that's what happens. So Armando drives from his home to the grocery store at a speed of 0.9 miles per minute. I think that might be important. For 4 minutes, stops for 2 minutes to buy snacks, then drives to the soccer field at a speed of 0.7 miles per minute for 3 minutes. The graph shows Armando's distance from home. So we could build that graph if we wanted. We know it's 0.9 per mile for 4 minutes, so that's how we'd get this first part. Stopping for 2 minutes, so his distance from home wouldn't change, and then his distance from home would increase again as he got through those next 3 minutes. Looks like the whole thing isn't shown for us here. We'd actually need it to go to 9, but we get the idea. Actually, I do want this, to go to 9. I don't know why they did that, but you can go ahead and extend it. There we go. Okay, so that would be 9 minutes. 3 different sections in the graph show there's 3 parts to the function. That's going to be important because we're going to need 3 sections when we write the function. And then we're just going to go through together how we write the function. So we determine the function rule for the first 4 minutes from 0 to 4, including 0 and 4, because we know he has to start at 0, and he actually drives for the complete 4 minutes. And that tells us it's the speed in miles per minute. Luckily, I already made a note about that up here. So it's 0.9 miles per 1 minute, or just 0.9. So that's the slope of that first part. Let me just adjust. Bear with me momentarily. There we go. So the slope is going to be 0.9 for that first line. Our y-intercept is where we start from. Well, he starts at home, so he starts at 0. So the function is y equals 0.9x plus 0, or just 0.9x. We don't usually write the 0 in there. You can if you want, because that's the y-intercept. So function rule for the next 2 minutes from 4 to 6, well, he's not going anywhere. So he's going 0 miles in 2 minutes, or just 0. So the slope of that one is 0. Let me turn the page. The function for the next 2 minutes is a constant function. That's why our slope was 0. And the constant y value is just where he was after 4 minutes. So after 4 minutes, he's at 0.9 times 4, or 3.6 miles from home. So in that 4 to 6 minutes, he's 3.6 miles from home. Now we need the function rule for the last 3 minutes. So again, the rate of change is his speed in miles per minute. And if you turn back to the page before, it tells you it was 0.7 miles in 1 minute, or again, just 0.7. The point that function begins at is at this 3.6 is the y, because he didn't go anywhere while he was getting snacks. He was just getting snacks. And we know that starts at 6 minutes, because it took him 6 minutes to get back on the road and head back to soccer practice. So this part I'm going to go through kind of quickly because I know you haven't seen this yet this year, point slope formula, but it's just a good review to watch in any case. What we're going to do is we're going to simplify this down so we get a slope and a y-intercept. So y minus 3.6, 0.7, and 6, we're just plugging in the point. We distribute the 0.7 and we get 0.7x minus 4.2. oops, I don't want minus 4.2 there. I did that too fast. I add 3.6 on both sides, and 4.2 plus 3.6, negative 4.2 plus 3.6 is 0.6. So the three parts then that we're going to plug in, so from 0 to 4, that was the first equation we got on the last page, right over here. Trying to find it, 0.9x. So it's 0.9x is the pieces between 0 and 4. Between 4 and 6, it's just equal to 3.6 because it was just a constant horizontal line there. And then between 6 and 9, it's this 0.7x minus 0.6. We'll work a lot more on building functions like this later, but I just wanted you to see sort of an example in context of how this works. So these pieces tell us the times that things are happening. These are also what we call domain restrictions. And basically what they're telling us is that we graph whatever's here in this domain. So we graph 0.9x when x is between 0 and 4, 3.6 when it's between 4 and 6, and 0.7x minus 0.6 between 6 and 9. Like I said, we're going to do a lot more with this. I know it's the first time you saw it. Don't get scared if you're confused right now. Stick with me. So first thing we're going to look at is evaluating piecewise defined functions, and that means like figuring out what number comes out. I'm actually going to skip this greatest integer function part for now. We'll come back to that in the next video, but for right now we're just going to skip that. So I'm going to skip all the way over here to example B on the next page. So example B on the next page, it says find f of a bunch of different things for this function. So let me just try and zoom in a bit more so you can see that a bit better. There we go. So basically what we're looking at here, this is the function in that purple box. And what we want to know is when f is -3, what the value is in the function. So if we start with that -3, what we have to do first is we have to look and see if it's less than 0 or greater than or equal to 0. So you look at what domain the value is in. So look for it in the domain. So you say to yourself, this is my x. Say self, is x less than 0? Why yes, self, x is less than 0. So since x is less than 0, I'm going to use this part of the function to evaluate it. So -3 is less than 0. That's what we just figured out right here. So we're going to use this -x. So f of -3 means where the x is here, I plug in -3. So I need -3, which is just +3. Now we look at -0.2. -0.2 is -0.2 less than 0? Yes. So we use this function again. So f of -0.2, the negative comes from right there. The -0.2 is because that's what my x is. And -0.2, let me just try changing. -0.2 is +0.2. Now, the next one is 0. So for f of 0, I say is 0 less than 0. We have to be a little bit careful here. 0 is not less than 0. 0 is less than or equal to 0, because 0 is equal to 0. So for 0, we're going to use the first function. We're going to plug it in here where the x is. So f of 0 is 0 plus 1, or 1. Then we look at 2. F of 2, so is 2 greater than or equal to 0? Yes. So we plug it in the second function. So f of 2 is 2 plus 1. Again, coming back always to this one. So 2 plus 1 equals 3. So to find the values, you just have to find the part of the domain it's in and plug it into the corresponding function. So let's do number 3 together. Again, we're going to skip number 2 for right now. This is supposed to be a your turn, but I'm going to go through it with you. if you would like to try it all by yourself first, you could pause now and then check after you try it and see how you did. So here's our function, negative x if x is less than 2, 2x plus 3 between 2 and 4, and x squared if we're greater than or equal to 4. So I look at my first x. My first x is negative 2. So I say to myself, is negative 2 less than 2? Absolutely. Since negative 2 is less than 2, I'm going to use this function for the first one. So I'm going to do negative 2, and my answer is going to be 2. If I want f of negative 0.4, I leave the zeros out just because I'm efficient. Negative 0.4. Again, negative 0.4 is definitely less than 2, so I need negative 0.4, which equals positive 0.4. So both of those were less than 2, so that's why I use this one. My next one is f of 3.7, and I'm going to switch colors because 3.7 is actually not less than 2. So I go to the next one and I say 2 is less than or equal to 3.7 is less than 4. Does that work? Why, yes. Yes, it does. So the function I'm going to plug into this time is 2x plus 3. So I'm going to do 2 times 3.7 plus 3. Well, 2 times 3.7 would be 7.4, I think. 7.4 plus 3 more, 8, 9, 10.4. And the last one I need is f of 5. So I say to myself, is 5 between 2 and 4? No, 5's not between 2 and 4. 5 is greater than 4. So the function I need for that one is that last one. So I'm just going to switch colors again. So f of 5, I'm going to use this function. And I'm going to need to do 5 squared. And 5 squared is 25. So we're always thinking about where the x, remember the x is this number in the parentheses, so which of those parts does it fit in? And that's how you figure out the value. Oh, you can't see 10.4. Now you can. So hopefully if you tried that on your own, you got it, and you're good to keep going. And next we're going to look at graphing piecewise defined functions. So the way that they show you to do this is by making a table of values. This is actually not my favorite way to graph piecewise defined functions, so I'm going to show you another way. Making a table of values is okay. The problem is it doesn't really show us like where the breaks are and how we get the pieces. If you remember when we did some graphing review earlier this year, and we actually did some problems where we had a limited domain. I think we did 2 of those. Basically, when you're graphing a piecewise defined function, you're doing that multiple times. So the big ideas, and I'm going to try to fit them over here. Step 1 is to graph the functions on the same grid. So you graph all of them together. I'm actually going to pause right now. I'm going to write them all out and then come back. I know it wobbles when I write, so you won't even know, but in a moment they will all magically appear. And now all 4 steps have magically appeared. So you may want to pause, obviously, and write them down. I'm going to talk about them. You probably will have enough time to write them while I talk. So we graph the functions on the same grid. We identify the domain restrictions, and I'll show you how to do that. I use vertical lines when I'm doing these. We erase the parts of the graph that don't belong, or you can bold the lines that do belong if you prefer to write in pen. And then you put in any endpoints. So those are the open or closed circles or the arrows that go. And I'll show you where those come from as well. So if we look at this first one, I'm just going to do this in pencil right over where they've done it so you see where it actually comes from. So f of x equals negative x. The first thing I'm going to do is I'm going to graph these 2 functions. So negative x has a y-intercept of 0 and a slope of negative 1. So if I were to draw that graph, I would put these points here and these points here, and then I would connect them all with a straight line. And you should totally just be watching this now. Don't try to do it with me. Just watch, because you already have the answer anyway. So negative x would go there. X plus 1 has a y-intercept of 1. and also a slope of 1. Remember, there's that hidden 1 there, just like that was hidden, and I'll put the plus 0 in. Sometimes it's helpful just to see it. So 1x plus 1, so we start at positive 1, we go up 1 over 1, up 1 over 1, up 1 over 1, and so on. And initially, I would have a line going in both directions. So if we just graph two functions, this is what our graph would look like. Now we want to look at the domain restrictions. And what I mean by that is we look at this part. So this part tells us that the first function is just less than 0. The second one's greater than or equal to 0. So 0 is my cutoff point. So I want to go along my x-axis till I get to 0. And what I like to do is just put in a dotted line. So I have a dotted line at 0. Now what I know, I have to use this and erase the parts that don't belong. And what that means is I look at this and I say, okay, when x is less than 0. So x is less than 0 is everything on the left side of that line I just drew. So everything on the left side of the line that I just drew gets drawn in with the first, dropping things. Everything on the left side of the line I just drew is this negative 1x minus, or negative x plus 0. So negative x plus 0 was this line. So I'm going to draw that one in, or if I'm doing it in pencil, I'm going to erase this one right from that 0. And I want to think about the endpoint. So it's less than only. So since it's less than, I want only an open circle right there at that spot. And then since it's less than only, that's why the arrow goes that way. So that's most of it. Then I just have to do the other side. So greater than or equal to 0 would mean from the 0 over. So that's this 1x plus 1. So that was this line. And that one, since it's or equal to, gets a closed circle. So again, if you're doing it in pencil, at this point you would erase that one. So notice you just have one line in each section that you've drawn. And you've graphed a piecewise function. Hooray! Let's do another one. Okay, so this one, we have 3 parts. So when we graph it, we're going to end up with 3 parts. I'm going to do it in pencil first, and then I can go over it in pen later. So my first part is negative 2x minus 4. So I'm going to go to minus 4 and put a point. My slope is negative 2. So from there, I would go down 2 and over 1. But I see pretty quickly I run out of room going to the right. So I'm going to go up and to the left so that I can get a pretty decent idea of what that line looks like. So that's my first line. Second one just says 3. Uh-oh, no slope. So really this means 0x plus 3. So 0x plus 3 means my y-intercept is 3. My slope is 0. So there, there, there. Hey, wait a second. That's just a horizontal line. Something like that. The last one, actually, I'm going to just label these as I go because it'll make my life easier in a moment. Next one's x plus 1. Put the 1 in to remember our slope is 1. Our y-intercept is 1. Go there, up 1 over 1, up 1 over 1, up 1 over 1. I know I'm graphing these linear equations pretty quickly. I feel like we've done a little bit of work with that already, so we should be okay figuring out, how to graph a line. So once I've got 3 lines this time because it's 3 parts, now I'm going to look at this. My cutoff points are negative 1 and 2. So on my x-axis, I'm going to go to negative 1 and put a dotted line, and positive 2 and put a dotted line. And what that does is that tells me now which functions to use in which part. So my first function was negative 2x minus 4, and I want that one when x is less than negative 1. So x is negative 1 is this dotted line. Less than that is everything to the left. So everything to the left of that gets this 2x minus 4. So that one, let's see, just less than. So I want an open circle right there. And then I want all of that going that direction. So eventually I'll erase the parts I don't need. I'm going to keep them for right now. Next one is this 3 between negative 1 and 2. both of those have equal to's under them, so I'm going to go -1, so the 3 was this line, color it in, connect it, and then finally x plus 1 when I'm greater than 2, so I come over here, my x plus 1 is this line I didn't use yet. So greater than 2, so it's from here over. That would have an open circle, but it's already colored in, so I don't need to worry about that. I'm just going to make this go off in that direction with an arrow. So you can see when we're done, if we erase all those other parts, that in each region you just have one function. So we have a piecewise function. We have graphed it. Very nice, very nice. Let's do one more. I think we'll let you try 7, but we'll do 6 together, just in case you need to see one more example. So in number 6, my first function is just x, or 1x plus 0. Again, I always graph the functions first, then do the domain restrictions, then erase the parts I don't want. So 1x plus 0, y-intercept of 0, slope of 1. Like that. That's 1x plus 0. Next one's 2x plus 3, y-intercept of 3, slope of 2, up 2 over 1, up 2 over 1. Let's see how straight I can make this. You know, if you ever can't hear me, I'm just mumbling, and you don't need to hear me anyway. And finally, -1/2 x. Ooh, -1/2 x plus 8. So I'm going to go to 8. Down 1 over 2, down 1 over 2, down 1 over 2, down 1 over 2, down 1 over 2. That's fun to say. Da, 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 da. And we have our 3 lines. Oh, I forgot to label them as I go. Not required, just helpful later. 2x plus 3. Just makes us think a little bit less later, which isn't necessarily a bad thing. So we look at our boundaries. 2, notice those are the same, and 4. So on my x-axis, here's 2, and 4, So I put in my boundaries. Now, for less than 2, I want the x, or the 1x plus 0. So less than 2 on the x is everything from here over. And I want the 1x plus 0, so I see up here that's this line. I'm going to follow that until I get into the range where I want it. So I want it here to there, and I look at this just less than, so it's open. Put an arrow at the end. Second part, 2x plus 3 between 2 and 4. So from here to here, I want this 2x plus 3 line. Whoa, that is way up there. That's okay. So at 2x plus 3 at 2 gets a closed circle. At 4 gets an open circle. Yes, indeed. And we color that in. And finally, greater than or equal to 4. So that's to the right of 4. We need the line we didn't use yet, or the -1/2 x plus 8. So that one's going to start here, greater than or equal to, draw the line and color it in, and there we are. So at this point you could erase the dotted line, or the pencil lines, but I think it's pretty easy to see on mine what the answer is. Okay, I would like you to try number 7 right now. Stop the video, try it. When you come to class next time, we will go through the answer together. Thank you very much for your attention, and have a wonderful day.